In the previous video, we discussed why the analysis of algorithms is important. In this video, we will learn formal ways to measure the order of growth or running time of algorithms. Since we are concerned about large input sizes, we need to study the asymptotic efficiency of algorithms. We will discuss some notational conventions to describe the asymptotic running time of an algorithm. These notations are always defined in terms of functions whose domains are the set of natural numbers. Using these notations, we can describe the worst-case running time function t, n, which is usually defined on integer input sizes. A function f, n, belongs to the set theta of g, n, if there exist positive constants c1 and c2 such that f, n, can be sandwiched between c1g, n, and c2g, n, for large n. Here c1 and c2 are positive constants. n0 is a positive value of n above which the condition c1g, n, less than or equal to f, n, less than or equal to c2g, n, holds true. The definition theta of g, n, requires that every member f, n, belonging to theta of g, n, be asymptotically non-negative. In other words, f, n, is non-negative for very large n. Note that there can be multiple functions f, n, for which the definition of theta satisfies. In other words, theta of g, n is not a single function, rather a set of functions. Thus, although we should write that f, n belongs to the set theta n, in practice we always write f, n is equal to theta of n. Consider the first problem where we have to show half of n squared minus 3 times n is equal to theta of n squared. We can check the condition for theta holds by putting c1 equal to 1 by 14, c2 equal to 1 by 2 and n0 equal to 7. However, we shall be able to tell the expression is correct without solving and simply by looking into it. Note that lower order terms of asymptotic positive function can be ignored while determining tight bounds, since these are insignificant when n is large. In this example, the second term on the LHS, that is 3n, is much smaller than the first term, that is half of n squared, when n is very large. Further, we should ignore all constants associated with the terms involving n. For very large n, half of n squared and n squared have same order of growth. Hence, for the expression half of n squared minus 3 times n, we should focus only on the term that has the highest degree of n, and we should not also see what constants are associated with this term. So, we focus only on the n squared term. The RHS is also n squared, and n squared is definitely theta of n squared. The second expression is not correct since the most important term on the LHS is n cubed, which is much higher than n squared for large values of n. Next, let us look into the big O notation, which provides only the upper bound. Look carefully into the second point. We have written 0 is less than or equal to f, n, which is again less than or equal to c of g, n, for all n greater than n naught. Here, c and n naught are positive values. This upper bound may be loose or tight. There is no restriction. But note that the lower bound of f, n, is not stated here. When we write f, n is equal to big O of g, n, we can only conclude that the running time of the algorithm f, n, will never be worse than that of g, n, for very large n. But through big O notation, we cannot provide a lower bound for the running time of f, n. Note that if a function f, n is big O of g, n, then f, n, must also be there in theta of g, n, since out of all functions that exist in big O of g, n, only a few will be included in theta of g, n. Thus, theta of g, n, must be a subset of big O of g, n. Any linear function an plus b is a big O of n squared, since the most important term on the LHS is n, which is definitely less than or equal to n squared for very large n. We can also say an plus b is equal to big O of n. N is a tighter upper bound for an plus b compared to n squared. Like upper bound, we also have another notation to define the asymptotic lower bound, which is big omega. Carefully look into the second point. For positive constants c and n naught, 0 is less than or equal to c times g, n, which is less than or equal to f, n, for all n greater than n naught. The lower bound defined through big omega may be tight or loose, and similar to the discussion in the previous slide, theta of g, n, is a subset of big omega of g, n. Further, if a function f, n, is both big O of g, n and big omega of g, n, then it must be in theta of g, n, since it implies that f, n, has the same order of growth as g, n, for large n. The reverse is also true, that is, if f, n is theta of g, n, then it must be big O of g, n, as well as omega of g, n. As discussed before, the asymptotic upper bound provided by big O is not necessarily tight. For example, we can say n is equal to big of n to the power 100. A tighter bound than n to the power 100 is n to the power 50. An even tighter bound is n to the power 10, and so on. We will learn another notation small o to denote upper bound that is not asymptotically tight. Carefully look into the definition of small o of g, n. A function f, n, is in small o of g, n, if 0 is less than or equal to f, n, which is less than c times g, n, for positive c and all n greater than or equal to n naught. Note that in the definition of big O of g, n, we had the condition 0 is less than or equal to f, n, which is less than or equal to c times g, n. This equal to in f, n, less than or equal to g, n, basically meant that g, n, was also allowed to have same order of growth as f, n in big O notation. This is not allowed in small o. So, small o can represent only loose upper bounds. As we can see in the example 2n is equal to small o of n square. It is also small o of n cube, but it cannot be in small o of n. Thus, although 2n equal to big O of n is correct, 2n equal to small o of n is incorrect, since n is asymptotic tight upper bound for 2n. Similarly, we have a notation for loose asymptotic lower bound, which is small omega. The concept is similar to small o, but this refers to loose lower bound. I hope it is understandable why n squared by 2 is small omega of n, but n squared by 2 is not equal to small omega of n square. Finally, if f, n, belongs to small omega of g, n, then g, n, must be in small o of f, n. The reverse is also true. This slide shows expressions for growth rates increasing from bottom to top. F, n, equal to 1 means the algorithm runs in constant time, which is the best possible running time for any algorithm, in f, n, equal to 2 to the power n means the algorithm runs in exponential time, which is very large. We will always look to develop efficient algorithms, and we aim to make f, n grow as slowly as possible. Thank you.